Hello. So one of you wonderful people asked me about a differential equation and using Euler's method to approximate the solution. So I wanted to go through that process and then we'll compare it to the exact solution. And what I'll also do, sometimes with Euler's method, you get all these calculations and these numbers throughout it, and it's hard to visualize exactly what is going on. So that's why I'm going to use Desmos here rather than just writing out all of the steps. Okay, and so we have a differential equation that the slope is 2 times x times y. We have an initial condition that we're at the point 1 comma 2, and we are asked to approximate the solution at x equals 3, using an h value of 0.4. Okay, so when you're using one of the calculators in the classroom, you want to make sure that you are saving your answer and using the exact answer so that you don't get a rounding in step one that brings you further and further away from the solution. Because every time that you round, if you're using that as your next x or y value, then that's going to give you a wrong slope. It's going to give you an even more wrong next y value. So the process, because it iterates, the error will grow and grow and grow if you're not careful with it. So let's start with our first calculation here. Our first slope is just 2 times x times y. So our first slope is just 4. That means that our second y value is the process for Euler's method is that the y value for step n is equal to your previous y value, not n plus 1, n minus 1, because it's your previous y value, plus the slope times h. And the slope is always from the previous step. So what I'm saying is you take the previous x and y value, that's xn minus 1 and yn minus 1. You plug those into the derivative to give you the slope. You multiply the slope by your horizontal movement because multiplying slope times horizontal movement gives you the change in the y value. Okay? So let's look at that process here. Our new y value is going to be our old y value of 2 plus our slope of 4 multiplied by our h value of 0.4. So now we have 3.6. Okay, great. So then we calculate our slope again. Our slope is always 2 times x times y. Remember that we used our h value of 0.4 right here. And so our new x value is 1.4. And our new y value is 3.6. Okay, so what I'm going to do also is show you on the graph that we started at the point 1 comma 2 right there. Let's zoom out a little bit. So there's 1 comma 2. We used our slope to get a new y value of 3.6, and we used our h to get a new x value of 1.4. Okay, so that's our 2 points right there. And I could connect those with a line segment if I wanted to, using like point slope form, where I could say y minus 2 equals 3.6 times x minus 1. And I can even restrict it so that this line segment only goes between 1 and 1.4. And so that little line segment is an approximation of our differential equation. Remember, the solution to a differential equation is a curve, and we're using line segments to create that approximation. So anyway, I now have a slope of 10.08. I got 10.08 by plugging in my new x and y values. And so then I can predict what my next y value is. My next y value is the old y value plus my new slope, 10.08, times my h value of 0.4. So that's my new y value of 7.6 0.632. So I have 1.8 because I added another h. That's my new x value. I'm going 0.4 steps further to the right. 7.632. That is my new point. And I can create the line segment y minus 3.6 equals my slope 10.08 times x minus 1.4, restricted between 1.4 and 1.8. Okay, then let's keep going with this process here. We need to do a new slope. So the slope is 2 times x times y. And I'm just going to copy exactly what I had, 7.632. So I have 27 point, that's my new slope, 27.4752. And so then I have my old y value, 7.632, plus my slope, 27.4752, times my h value. See how it's the same process over and over again? So that is now my new predicted y value. So I'm at 2.2, comma, 18.62208. Looks like I'll need to zoom out a little bit more. I can connect those again with a line. Y minus 7.632 equals my slope, 27.4752 times x minus 1.8, restricted between 1.8 and 2.2. Okay, there's just a couple more steps here. We're going to use our new 2 times x times our new y, which I'm going to just copy from here. So as you get going, it just becomes so easy to make errors. So please just use copy and paste or use the saved answer function on your calculator. So my new y value is my old y value plus, watch how I do this. I can grab my entire slope times h. So that's my new y value. We are skyrocketing here. Okay, so we are going to have a new y value of 51. And so we're now at the point 2.6, comma, all of this stuff. Oops. Let me see if I can grab it. There we go. 2.6, comma, all of this stuff. We can label that. Great, you can see it's right there. Okay, then I'm going to find one more new slope, 2 times the x value of 2.6 times the y value that I just copied in there. That gives me a slope of 267 and change. And that means my new y value is my old y value that I just copied and pasted, 51, plus all of this is my new slope times 0.4. So my last y value that I get a prediction of is 158. And so that's when x equals 3, y is equal to. So as the calculations got crazier and crazier, I stopped typing it all in and I just started copying and pasting. Okay, great. So that's how you get your solution. So I guess that we're predicting about 158 for when x is equal to 3. Just real briefly to show you how you would solve it analytically, you would write dy dx is 2xy, divide by y to separate the variables, multiply by dx, integrate, natural log of absolute value of y equals x squared plus c. That means that y is equal to a e to the x squared. And because my initial condition is positive, I don't need the absolute value bars anymore. If I use my initial condition of 1 and 2, then I can see that 2 equals a times e. So 2 over e, or 2e to the negative 1, is a. And so I should be able to get a good approximation if I type in y equals 2e to the negative 1, that's my a value, and e to the x squared. And let's look at how close we got. Yeah, I mean, you can see that the red or the black graph goes really close through those dots, and in fact, it's not so bad. So if I look at when, yeah, see, we're just so close to the line right there. And if I look at this equation here, and I just copy it down and plug in x equals 3, it's a lot bigger. That's funny. So even though they're so close to each other horizontally, the exponential curve grows so fast that this is a severe under approximation. Okay, so it would have been a better approximation if we had used a smaller step size. Using a step size of zero point 0.4 is kind of egregiously large. So anyway, that's the process. Please use copy and paste, and I also hope I didn't make any copy errors when I was typing things in. All right, please let me know if there's anything that was confusing, and I'm happy to help out.